Hi guys, so we're just about to begin, so just sit tight and we're also streaming this conference on YouTube. The link is in our bio to our YouTube and yeah, so go check it out if that works for you guys as well. So, as everyone is settling in right now, we do have a lot of people still waiting to join. So, let's wait about 3 to 4 minutes approximately. Just a little switch on the YouTube stream. We have put it in the chat box in the Google Meet right here. And it also is in our Instagram bio. So, you guys can check that out if that's working for you.
Okay, it seems as though a lot of people are here, so I feel like we can start just so that we can stay on the clock. So, hi everyone, my name is Simran Singh. I'm 15 years old and I am the president and founder of STEMPOWER, and I'd like to welcome all of you here today to STEMPOWER's very first virtual STEM-based conference. Okay, so as most of you probably already know, the goal of STEMPOWER is to provide high school students with these STEM-related resources in the forms of these informative webinars, and our big goal in the future is to actually hold a big in-person conference where we can have little workshops and panels and all that type of stuff. But right now, due to COVID, that is not allowed, but in the future, that can be a possibility. Okay, so let me just give you guys a quick little rundown of how today is going to work. So first we will have our introduction. So we will introduce our executive team and then our panelists for today. Then we will have our discussion segment. So some personal STEM related questions and then some directed questions, which were compiled by our attendees registration forms. And at the very end, there will be a Q&A session where the attendees can ask whatever questions you have to our panelists through the chat box below. And if you're watching from the YouTube live stream, you can actually drop your questions in the live stream chat as well, because our executive team is monitoring all of the questions to ensure any questions you may run into get answered by our panelists. Okay, so it's time for you guys to get to know our executive team. So STEMPOWER is made up of 10 very hardworking individuals. We were all given different tasks and roles. We all worked together to ensure that this conference ran smoothly. So unfortunately, just to make sure we respect the amount of time that we have, we will be unable to have each member introduce themselves. But if you'd like to get to know our team even better, you can check out our website for that. Okay, so let's dive right into our panelist introductions. So firstly, I would like to welcome Dr. Allison Kelvin. So Dr. Kelvin is currently working towards developing a vaccine for COVID-19. She's testing on animals to see how the virus is transmitted from one to another and how our body reacts to it. She's also working towards developing a universal vaccine for the seasonal influenza virus. She's also a virologist at Dalhousie University, an assistant professor in the Department of Pediatrics, as well as a member of the Canadian Centre of Vaccinology. So, Dr. Kelvin, would you like to say hello to STEMPOWER's attendees today?
Hi, everyone. Thanks so much for having me. So that's all correct. I'm a scientist at the Canadian Centre for Vaccinology, and I'm working on a COVID-19 vaccine. Although right now I'm at Vito Intervac, which is at the University of Saskatchewan, where I'm able to work with the SARS-CoV-2 virus and because they have a high containment facility. So we work with the virus in kind of big spacesuits, and I'm happy to be here and discuss any aspects and questions that you guys have about my work or about careers in science.
Okay, thank you so much, Dr. Kelvin. So our second panelist for today is Dr. Maria DeRosa. So Dr. DeRosa is a full professor in the Department of Chemistry here in Ottawa at Carleton University. She is also working towards different things such as DNA, nanotechnology, as well as nanomedicine, as well as aptamers. So she works with how aptamers work and how they can be used to fight and detect different illnesses. So Dr. DeRosa, would you like to say hello to STEMPOWER's attendees today?
Certainly. So thanks so much for having me here today. You heard my name is Maria DeRosa, and I'm in the chemistry department at Carleton. And yes, we work with DNA, but we use it in a kind of unusual way. We use it as a building block for new sensors, for new drug delivery, and for things like diagnostics. So I'm happy to answer questions about the research that we do or anything related to science.
Okay, perfect. Thank you so much. So our third speaker for today is Dr. Matthew Holohan. It looks like it's lagging for me, but I hope you guys can see it. Okay, so our third speaker for today is Dr. Matthew Holohan. So Dr. Holohan also works at Carleton University here in Ottawa in the Department of Neuroscience, and most of his research revolves around developing a novel treatment for Parkinson's disease, as well as analyzing the in vivo and ex vivo effects of concussions on the brain. So Dr. Holohan, would you like to say hello to STEMPOWER's attendees today? It's lagging a little bit for me, but I'm not sure if you guys can hear it. I can leave the call and rejoin and then see if it works better.
Hold on, there we go. Am I unmuted now? and see it down at the bottom. So yes, hi everybody. I'm Matthew Hallahan, sitting in my basement in Ottawa, and I just would like to say welcome to all the participants and to say how really I'm impressed I am that you're all here on a nice, Monday afternoon before school starts. It's really great to see all these keen students interested in learning more about STEM. So I hope we can have a good conversation. Thanks for having me.
Okay, thank you so much, Dr. Holohan. So it's working better for me now. So I think we can get to our fourth panelist for today, who is Professor Jason Bell. So Professor Bell is from the University of Waterloo in the Pure Mathematics Department, and most of his research revolves around non-commutative algebra as well as number theory. So Professor Bell clearly knows a lot about mathematics and numbers and all that type of stuff. So Professor Bell, would you like to say a couple of words about your life outside of the mathematics department?
Can you hear me? Okay, so I'm very happy to be here. You asked about my life outside of the math department. It's pretty much spending all my day inside, so I don't have that much of a life. But I'm very happy to be here. I think it's a great thing that you guys are doing, or you people are doing, so that's wonderful. So hello, everyone. I should mute myself, right?
Okay. Thank you so much. Yeah, okay, perfect. So our final panelist for today is Dr. Spiro Karagianis. Please tell me if I pronounced that wrong. So our final panelist for today is Dr. Spiro Karagianis. He is also from the University of Waterloo, and he is an associate professor in the Pure Mathematics Department. Most of his research revolves around differential geometry as well as geometrical analysis, and he is also a member of the Geometry and Topology Research Group, where they hold these weekly seminars talking about the connections between geometry and physics and overall just very math-related stuff. So Dr. Karagianis, would you like to say hello to STEMPOWER's attendees today? It seems as though it's lagging a lot for me, so I'll just join the call again to see if it works better. Okay. I had to leave the call, but did you have the time to introduce yourself to our attendees, Dr. Karagianis? Okay. Maybe if your connection gets better throughout the presentation, you can just hop on in and speak about yourself and just a quick little introduction, and we can get to the next part. And when we ask our directed questions, maybe then you can try again. Okay, so now it is discussion time. Is that better? Can you hear me now? So let me just give you guys a quick little run to work. Okay, so for this segment, we will have our three main overall topics, which are going to be the STEM-related questions. Then we will have our directed questions, which are more of the Q&A most frequently asked questions, which were compiled by our attendees' registration forms. And at the very end, there will be the follow-up session where any attendees can ask whatever questions they have in the chat box below. And I should also this segment is actually ongoing. So attendees, if you have any questions at all, you can just drop them in the chat box below, and our panelists will try as hard as they can to answer them as soon as possible. We're going to be talking about today are career inspiration, any difficult one highlight, or your favorite project. So our very first question, and we were thinking maybe Dr. Karagianis, if your microphone is working, would you like to start us off for this one? So what inspired you to choose a career in the field of STEM?
Sure. Can everybody hear me now? Yeah, I don't know. I was using a headset, which is supposed to work better, but it doesn't. So no.
Yeah, I can hear you.
Okay, great. So
if you'd like, you can introduce yourself first.
I did before, but maybe people didn't hear me. Yeah, my name is Spiro Karagianis. I'm an associate professor in the pure math department at Waterloo, and I've been there for over 10 years now, and I work in differential geometry, which you'll probably hear a little bit more about later in the webinar. So what inspired me to pursue this career? Well, there was no single person who inspired me. I didn't really know anyone who was growing up as a child who was a mathematician or even really a scientist. I didn't even know this kind of a career existed. But it was a gradual evolution. As I grew older, I learned more and more on my own, mostly, and found my path towards here. And when I was a little kid, I wanted to be an astronaut because basically watching movies like Star Wars, I thought that's what astronauts do. And then, as I learned more, I thought, okay, what I really like is astronomy and astrophysics. And I learned more about that, and I realized maybe physics is my calling. And then I learned even more, and then I finally settled on math. But that didn't really happen until the middle of my undergraduate career. So, I always knew I wanted to do something. Exactly what that was kept changing as I grew up and evolved. But everyone has a different story, right? So that was mine.
Okay, well, I think you finished speaking. I think you cut off maybe, but that is very inspirational, and I'm inspired by what you had just said about how you chose your career. And we were thinking, Dr. Holohan, would you like to go next for this question?
Okay, guess I'll try to keep it limited. I was thinking, I guess if we're going to go back further in time, I was actually initially, so I'm from the US, and so I was initially interested in going into the FBI because there was a lot of TV shows on the FBI. I also watched a lot of Star Wars, but I never thought that I could ever travel to a galaxy far, far away. So something a bit more locally like the FBI seemed right. And then when I was going through high school, I actually really enjoyed English literature for some strange reason. It's a bit of a shift from where I am now, but I really actually did like writing, creative reading. But then when I went to university, it was kind of, I didn't know what to do. So I just chose psychology because it seemed like it was a major that would encompass everything that I kind of wanted to do. And I took chemistry and physics because I was doing a Bachelor of Science. And I loved it for some reason. I really enjoyed physics and chemistry. And somebody said, well, maybe you should go the pre-med route. So I started going kind of pre-med, but then I took a behavioral neuroscience course in the psychology department, and I just loved the brain. And that was my third year of university. And that's when then I just started taking neuroscience courses, neurobiology courses. And I worked in the field for a little bit, and I was inspired by a lot of people who were around, and they said, pursue this, go to graduate school. And so here I am, 20 years later, still studying the brain.
Wow, that's very cool, your whole story of how you decided to choose your current group that you're in. So we were thinking, Professor Bell, would you like to go ahead for this question? What inspired you to choose your career in this field of STEM?
Okay. So actually a little similar to Spiro's story. I wanted to be an astronaut too as a kid. I didn't necessarily think being an astronaut would be like being in Star Wars, but I had some some thought of going, to see the moon or something like this. And then I think as I wanted to really understand how the universe works, and I still do, but I've sort of given up on that hope. But I realized that to do so, you needed to know some mathematics. And I think at some point I just transitioned. I wanted to, learning mathematics for its own sake became more interesting to me than the original goals. So then it was just a very natural path to, I wanted to learn as much mathematics as possible, and I just kept going. So I ended up here.
Oh, wow, that's
Go
very
ahead.
cool. It seems very similar. All of the mathematicians like to go.
Yeah, I should have said I was done. Sorry, that was awkward.
Oh, it's okay. Don't worry about it. Okay, so we were thinking, Dr. Calvin, would you like to give your take for this question? What inspired you to choose your career of lab research and all that type of stuff?
Sure. So actually, I was really interested in space as a child as well. But I was born in the early 80s, so which was right around the time of the emergence of HIV and the AIDS pandemic as well. So at that time, I was really interested in what was this microscopic pathogen or virus that was causing people to be sick. So I always had this vision of me in a spacesuit or a virus covering that looked like a spacesuit, working on something, a deadly virus, and trying to understand how this was making people sick. So that was kind of my original inspiration. And when I got into undergrad, I was really enjoyed doing scientific projects and asking questions and trying to answer them. And I really realized I wanted to ask virus-related questions when one of my lab mates turned to me one day and said, "I really love a man in a suit." And I said, "So do I. I would also love to wear a suit, one of those big suits that you wear when you're working with viruses." And of course, she was talking about a formal suit and a man all dressed up. And I was really thinking about how I wanted to continue my career in science. So that's kind of where it started. And I really love my job today and how it applies to the current pandemic situation. And that's about it.
Okay, thank you so much. That's a really great story. I think most of us have seen that famous picture of you in the big like hazmat suit where you're about to go into testing something. I've seen it. I've definitely seen it. Okay, Dr. Rosa, would you like to finish us off with this final question? What inspired you to go into your career in STEM?
It's a good question. And actually, I think it's very funny that I can say that I was also interested in being an astronaut. And I even applied when they were asking for astronauts. Maybe it was like 15 years ago. I actually applied. I made it all the way to the point where they said, "How much fighter pilot training do you have?" And I said, "I drive my car very fast." And that's as far as I got in that process of finding the next astronaut. So as a kid, I loved everything to do with science, but I loved all kinds of things. So I think similar to Matt, like I loved English class, I loved math, I loved science, I loved all kinds of things. I loved school. So I didn't really know that I wanted to do science until I started doing science. So it really wasn't until, even third year university where I had a chance to work in someone's research lab over the summer. And I actually got to try an experiment. And it wasn't just an experiment out of, a lab book. Here, mix A with B, you're going to get C. It's going to change color, write down your observations. It was, "Okay, Maria, we have this question. We don't know how to answer it. Here are a few things to try. I have no idea how that's going to turn out. Let me know how it goes." And so that kind of freedom and that idea that I could generate an answer that no one has generated before. I could make a molecule that no one had made before. That was so exciting, and I was hooked. So it was really after that experience of actually being in a research lab that I knew that I wanted to do something like that for the rest of my career. So that's my answer.
Okay, that's very inspirational. Yeah, definitely working in the lab setting, it's really cool being able to work with all different chemicals and everything. And I'm very fortunate to be able to work with you and Dr. Holohan as well as Dr. Abasade, just working in your laboratory and being able to run different tests. Okay, so our second question, we were thinking, Professor Bell, would you like to start us off for this one? What are the difficulties that you faced throughout your career, if you faced any, and how did you kind of control them and just stay motivated?
Okay. So I was thinking about this, and I realized I think in academia there's sort of this sort of incremental increase in how difficult academic life becomes. So, you know, you start as an undergrad and there's some difficulties with that, and then you go to grad school and there's whole new challenges, and then you're a postdoc and you have to teach and do research, and there's always just added expectations. So I think there's always these new difficulties that arise, you know, and eventually, you know, you're doing things like, you know, editorial work and things that you're not even trained for, and those are difficulties as you get higher in the career. So I think because it doesn't happen all at once, it's somehow manageable. But there are these sort of difficulties that you encounter, and how do you deal with them? You just have to either seek out some help if maybe you have a mentor or something like that. That is one way. Other than that, you know, you just have to hope that you can get it done, and usually you can if you put in the time. So this time I am done. Okay, so I'll turn off my microphone.
Okay, thank you so much. That was a great story and how you were able to just push through all of your difficulties and just being able to stay motivated and stay on track. Okay, so we were thinking, Dr. DeRosa, would you like to start us off with this question as well? What were the difficulties that you faced throughout your career, if you faced any?
Yes, lots of difficulties, and just to keep it brief and also positive, it's good to stay positive. I think, you know, in a research-based career, you face a lot of failure. So in school, you know, you are sort of trained. If you study, if you put that time in, if you put the effort in, then things are going to work out. When you do research and you're exploring new things, a lot of times your ideas won't work. Sometimes you write up something that you've done, and you submit it to a journal and they reject it. Sometimes you have a great idea and you ask for money from a funding agency and they say, no, that idea is bad. So all those kinds of things, at first, it's hard to face all that rejection, but eventually you get used to it. And also you sort of realize that a lot of times, hey, you know, when they rejected this paper that I submitted, for example, they had a lot of good suggestions. And so now the paper that I ultimately publish is better, or the idea that actually gets funded is a better idea, or something like that. So you have to kind of, you know, not take it personally and just use it to improve and to build on it. And if you can overcome that, then usually things do end up working out. You just have to be able to face a little bit of that rejection that you maybe weren't used to in your regular academics. And that's my answer.
Okay, that's very true. You do face a lot of failures when you're working in the lab and all that type of stuff, but it's great that you were able to just push through and stay positive, as you always are, and just be able to stay on track. So Dr. Kelvin, would you like to give us your take for this question? What were any difficulties that you may have faced throughout your career?
Sure. So I am a female researcher, a female scientist, and with that, I've heard many upsetting things from both male and female researchers. And also, it's a bit of a barrier being a mother in science. So I'm a mother as well as a scientist. And to start with being a female in science and the things that I've been told during my research career, to push through that is to know that how much I love coming into work every day and how much I believe in the work that I'm doing. And if you have that inside of you, I think that the truth will come out, and science needs diversity. So that kind of leads into the importance of keeping mothers inside science as well as other people who are diverse. And it takes different perspectives to solve different problems. So one of my biggest research findings was that the lactating mammary gland can be susceptible to influenza virus infection. I feel like I wouldn't have discovered that if I didn't have personal experiences of breastfeeding and having my own children. So I think it's really important that we continue to keep science diverse and flexible for different types of people. And that's about it.
Okay, thank you so much. That was actually very inspiring. We were planning on having a woman empowerment segment for our conference, but we would have ran short on time, but that was a very great response. And that actually probably inspired so many other females that are trying to go into STEM, but have heard so many negative thoughts, but they just pushed through and they were able to just stay positive and on track. So thank you so much for that, Dr. Calvin. We were thinking, Dr. Karajanis, would you like to give your idea
Sure.
of any difficulties you may have faced throughout your career?
Sure. First, I want to agree exactly with Maria that you really have to be able to take rejection if you're a scientist. We all get rejected. We've all had papers rejected. We've all had grants turned down, and you can't take it personally. You need a bit of a thick skin to do this job. But the other thing I would say is, and this it's probably also true in all the fields, but certainly very much so in math, is that when you're doing a PhD, that is kind of a little bit of a dark time, because every PhD student at some point goes through some self-doubt, saying, why am I spending 4, 5, 6 years doing this when I don't know if I'll get a job after, and if I do, I'm going to start out making much less money than my friends from high school who are already in the workforce. That's true, but you just have to hang in there. If you really believe in what you're doing, if you really have a passion for it, eventually you'll be fine. You'll make enough money, and you don't have to worry about that. So it's also normal if you're thinking, I don't know if I can do this. I don't know if I'm in the right going in the right direction. You're not alone. Absolutely, everyone who's done a PhD has gone through that period of time. They've all had doubts. They've all said, maybe I should quit. And for some people, maybe it is the wrong path, and it's a time to discover that. But it's totally normal to have these doubts during the process. And that's my answer.
Okay, thank you so much. Yeah, I felt that though all of our panelists would have a very similar answer for this one, just to be able to have a thick skin and be able to just persevere and be able to reach your final goal, which is a very important thing that everyone should be able to take away from this conference today. Okay, and our final panelist, Dr. Holohan, would you like to tell us any difficulties you may have faced throughout your career?
Yeah, I mean, I would just reiterate what everybody else has said, in that, it's you do fail. There is failure. And I was thinking, I mean, I want to try to add something a bit different, as I have two kind of examples. I remember when I took math, in fact, in high school, since there are two mathematicians, and the answers were always in the back of the book. So you could always, look in the back of the book and say, oh, there's the right answer. Perfect. But in science, you don't know what that right answer is. And it's more of just taking that path and trying to, say, okay, well, where is this going? I don't know what the right answer is. And you have a right answer in your mind, and that could be wrong. So that's always a challenge to say, you know what, I was wrong. This is not the answer that I thought it was going to be. So you have to admit that you are wrong every once in a while. And I think one more challenge I'd just like to add is, you often find that you step out of your comfort zone. So I kind of, as I said, I started in psychology, and then I stepped out into more of just brain and chemistry. And then I stepped, the next in my postdoc, I went way out of my comfort zone into more molecular biology, as it applies to the brain. And so it was very uncomfortable that I had to relearn things. I was in my early 30s learning new information, learning DNA, RNA. So that's a challenge, but it certainly is a challenge I think that's worth pursuing. And it does, I think there are really big payoffs when you do step out of your comfort zone and take those challenges. So those are my challenges.
Okay, thank you so much. It's definitely a very good skill, I guess, to be able to admit that you're wrong to something and just being able to learn new things. So thank you so much for sharing all of your answers for that question. And we have one final question for this Q&A type of segment. And it is, what was your proudest moment or greatest achievement? Or you could just say a highlight in your career. And we were thinking, Dr. Kelvin, would you like to start us off for this one?
Sure. So, I mean, as it was just discussed, a career in science is full of ups and downs. So there's been a lot of ups, but I think always being a mentor and having my own students and seeing them succeed, seeing them hit that perfect presentation or answer a question with a deep, thoughtful analysis is always, to me, the greatest moment. So it happens a couple times a year, so it's not just one, but watching your students get it is really one of the reasons why I'm here. Yeah.
Okay, thank you so much. That's definitely very inspirational to all of the students that have mentors who are professors in universities, and it's just a really great experience for everyone overall. So thank you so much for that. And we were thinking, Dr. Holohan, would you like to tell us one of the highlights in your careers or one of your proudest moments?
Sure. So I think this follows up from some of the challenges where you always feel like maybe you're not the best, you're not doing right, things that you do are just not correct. I get a little bit underconfident, I guess, intimidated. So, so I think my most memorable achievement, and there's I agree that having students succeed is a great thing, having high school students come to the lab, but I think for me it was the renewal of my first grant. So when I first got a NSERC grant, I thought, okay, well, maybe I just got lucky, maybe they felt sorry for me, I'm not worthy. And then when I applied for my renewal and it was renewed, I thought, whoa, wait a second, somebody actually likes what I'm doing. Somebody feels the same, worth that I feel for my work. And so and this, it was not a huge thing in my career, but it was a very memorable moment. And I think I just felt like, wow, it's renewed. And now I felt established, and then, my career just could start rolling. So it's it's a nice feeling to have, that outside acceptance, I guess, for things that you're doing. So that's it.
Okay, thank you so much. Yeah, that's definitely a big confidence booster. It helps you stay on track and make sure that you keep continuing what you do and just staying and getting to that final goal, which is like the big prize at the end. So yeah, that's very inspiring. Okay, and we were thinking, Dr. DeRosa, would you like to tell us one of the main highlights in your career?
Absolutely. So the last two answers have been great, and I feel like similar stories for both. I would say that for me, my proudest moments have been to see my students reach their goals. I agree with Matt too, though. When someone actually tells you that your ideas make sense, I love that too. But yeah, so far I've had students who've been trained in my lab. They've done their PhD with me, and now I see them. They have their own research lab. They're taking the skills they learned from me and how I may have mentored them, and they're now passing it on to the next generation of students. So having that, I can't put a price on that. That's been amazing. Same thing goes for other students who sort of what you've already heard about, people who were doing PhDs and then they decided that maybe academics is not for them, and seeing some of them go on and succeed in other sectors that we weren't expecting, but they're doing amazingly well, and part of the training that I was able to give to them has been helpful. So the idea that you're doing this job and you're changing lives, who could ask for a better job than that, right? So I think that's been for me the proudest achievements, is seeing that other students reach their goals. That's my answer.
Okay, thank you so much for that. It seems as though all of our panelists are actually very proud of their students in their lab, and that's just a very great thing for all of you. So thank you so much for that. And Dr. Karagianis, would you like to give us a highlight from your career, one of your proudest moments?
Sure. I agree certainly with everyone that when we have a student graduate and do well, then we feel it's like being a parent, right? It really is. You feel like you've accomplished something and trained someone to continue on in their future. In terms of greatest achievement academically, in terms of my research, I like to believe that's still ahead of me. I don't buy into this common saying in mathematics that when you're over 40, you're over the hill. I'm not done yet. I'm still working hard. But my proudest moment, I just didn't think about saying this, and I just thought about it now. When I was in graduate school, in math, we always have conferences for the big mathematicians. We have conferences when they hit a big milestone birthday, like 60th or 70th. And when I was in graduate school, I went to the 60th birthday conference of my supervisor's supervisor. And I remember being in awe at all these big name people that were speaking there, and I think in attending the talks, and I couldn't understand half of what they were saying or more. And then 10 years later, at his 70th, I was an invited speaker. And I just couldn't believe that they had invited me. I was of course, very, very happy to be invited, but it almost seemed like this got to be some kind of a joke. This is a prank, somebody's playing on me. But it was real, and I was there, and I gave a talk, and it was probably the proudest moment so far of my academic career.
Okay, wow, that's very inspirational. Definitely, you were probably very proud of yourself and just very proud of how far you'd come at that time. So congratulations for that. And now we would like to have Professor Bell. Would you like to state your proudest moment or a highlight in your career?
Yes. So I think there are lots of things that feel, really good in academic life, like, organizing a successful conference, or you give a talk and people say, oh, it was really good, I really enjoyed that. Getting a paper accepted, getting a grant, all of those things feel great. But I agree that I don't know if I necessarily take pride in those things. They feel good, but it's a different feeling when you mentor someone and you see that you make a difference at a human level. And I think I first felt that too when I was, teaching my first course and, interacting with the students and really making a difference. So I think those are the things that do give a feeling of genuine pride. So I agree with that, yes. And that's my answer.
Okay, thank you so much for all of you for answering our STEM-based personal questions. And I think it's time to dive into our directed questions segment. So this segment is more, each panelist will have very specific questions for their own specialty. So for example, our first couple of questions are for Dr. Kelvin. And since you work with COVID, viruses, basically lab research overall, that's where most of your questions have come from our attendees. So our very first question for you today are, what are the steps that must be taken to develop a vaccine for a disease, and what, in your opinion, is the hardest part?
Yeah, that's a really great question. So when we think about a new virus like SARS-CoV-2, so I work on emerging viruses, and that means that the next big one is on the horizon. We really can't predict it. And so just as with SARS-CoV-2 is completely new, when you have a new virus emerge, you know nothing about it. You don't know what family it belongs to. You don't know the nucleic acid sequence. You don't really have an idea of how it's making people sick and what that disease looks like. Is there a fever? Is there a rash? So step one is always identifying what that virus is. Step two is understanding how it's making disease, but we need to know, to make a successful vaccine, how we can block the virus from actually infecting a person. And with that, it's identifying a target on the virus. For SARS-CoV-2, it's called a coronavirus because it's kind of a ball with all these spikes coming out of it, which is the corona or crown of the virus. And those spikes bind to receptors on our own cells, and that's how the virus gets into the cell. So those spikes actually become a really great target for vaccine development. So after a vaccine target has been identified, we can start building the tools of the vaccine. So really, the hardest part is the beginning, understanding what the virus is and identifying a target that we can make a vaccine from. The next part is understanding if the vaccine can actually be protective. And we have what's called correlates of immunity to understand if our immune response is making a protective is responding protectively, and usually that's through antibodies that can, in this case, bind to the spike protein and block it from infecting cells. So antibodies are secreted proteins from B cells, and we can actually quantify those proteins after we've been vaccinated. So that's kind of the process of developing a vaccine. And the big hurdles are identifying the target and then evaluating if that vaccine is actually producing the protective response or correlative of immunity. And yeah, that's what I think about question 1.
Okay, thank you so much for that. I think that you broke it down in a very simple way so that all of our attendees would be able to understand. And I think now we'll, take more caution when going outside and doing all of that type of stuff. So our second question for you today, what is the biggest difference or challenge that you faced while trying to create this vaccine for COVID, as well as for the seasonal influenza virus? So in short, what was the main difference and the biggest challenges that you faced?
Right, so SARS-CoV-2, which causes COVID-19, is a coronavirus, and it's a positive sense RNA virus, which is different than influenza family of viruses, which are negative sense RNA viruses. And because influenza viruses are negative sense RNA viruses, they actually make a lot of mistakes when they're replicating during infection, when they're inside of you. So they mutate quite quickly. And that's why we're always behind with our vaccine development for influenza viruses. But for COVID-19, our biggest hurdle was that we had never seen this virus before, as I mentioned previously. So we had to figure out how we could target this virus. Because it's a positive sense RNA virus, it's actually a really big, has a big genome, which includes a proofreading mechanism. So if it makes a mistake while it's copying and replicating, it can go back and fix it. So it's a bit more stable. So I'm not predicting it having the same problems as the influenza virus. But again, the biggest hurdle was identifying what our vaccine target was and then building the vaccine from ground up at this lightning pace because we want to beat the virus as it's spreading all over the world.
Okay, thank you so much, Dr. Calvin, for all of the work that you're doing just to save lives and just make sure that everyone stays safe. So thank you so much for all of your answers. And our next series of questions are for Dr. DeRosa. Now, since you work with aptamers and nanotechnology and all that type of stuff, that's where most of your questions are coming from. So the first question for you is, I would just say, what are aptamers? How are they made? Kind of what's the difference between aptamers and antibodies? And in your opinion, it'll totally be very biased for you, but aptamers or antibodies, which one is better?
Hi,
Great
Simran.
question.
Sorry, Dr. DeRosa, just right before we continue, I'd just like to thank you panelists for all your amazing answers and amazing questions. If we could just try to ask both questions together, Simran, and maybe limit our answers. Unfortunately, because this conference is so short, we're running out of time. So it would be great if everyone could just continue, but a bit quicker. Thank you very much.
No problem. Thanks for the heads up. And yeah, so it's actually, yeah, I'm happy to answer the question quickly. So aptamers are small pieces of DNA or RNA, and they're synthetic. And what's interesting about them is they act like antibodies. So you heard about antibodies, they're proteins, they bind to things. So you heard about it binding to the spike protein in a virus. aptamers are found by a lab experiment, and they're able to bind to anything that we set the experiment up for. So if I want to find an aptamer that binds to a protein, I set up an experiment, and then I'll end up with a sequence of DNA or RNA that folds up into some kind of nanoscale object shape that's able to recognize and bind to a target. So we're interested in using them for all kinds of different things. So we're actually working on a SARS-CoV-2 aptamer that's going to be used for diagnostics, not as a vaccine, but as a diagnostic. We're working with Dr. Holohan on an aptamer that's going to potentially bind a target related to Parkinson's disease. So they're very versatile, and you say, aren't they the same as antibodies, aptamers versus antibodies, which one's better? They're both excellent at their jobs. And what's nice about aptamers as opposed to antibodies is just that they are synthetic. So I can make them in the lab, I can purify them, and I can play with them in a way that's harder to do with antibodies that are coming from a living system. So nothing's impossible, but aptamers just have, they're just more tractable, they're more easily modified. And so they're easier to implement into nanotechnology. So I think the future for aptamers is bright. We can do all kinds of interesting things with them, and that's what we're trying to do. So those are my answers to both questions.
Okay, thank you so much, Dr. DeRosa, for explaining the difference between the two and just clearing the air between both of them. Okay, so our next series of questions, I'll try and just merge them together, are for Dr. Holohan. So since you work with the brain and Parkinson's and all that type of stuff, our questions for you is, what have you discovered through your research about the in vivo and ex vivo effects of a concussion on the brain? And do you believe that some people are just normalizing the very alarming symptoms of Parkinson's disease?
Right. So just in terms of time, I was trying to, because I had seen these questions, I was trying to think if I could merge them together. And I think one of the important things is trying to understand what conditions set up pathological outcomes in the brain. So in concussion, is it a particular age group that if you get a hit on the head, do you have worse outcomes? Is it sex? Is it female or male? Is it some other condition that we're not aware of? So maybe you have a cold, or you have, some viral infection. So, what are those conditions then that say, okay, if I get hit on the head, I'm going to have worse outcomes, worse concussion symptoms. And the same kind of applies to Parkinson's disease. So when I see this, if they're normalizing the symptoms, I think what you almost want to say is, are they ignoring the prodromal symptoms? So in Parkinson's disease, it's pretty well known that it's a motor disease, so people show that characteristic tremor at rest. But there's a lot of symptoms that start to appear sometimes 20 years before those motor symptoms appear. So there's peripheral, so constipation, there's sleep disorders, there's depression. So it's, are people not looking at those symptoms, those prodromal symptoms, carefully enough to say, well, this is actually now going to predict my Parkinson's disease? And with Dr. DeRosa, that's what I think we're trying to do, is say, well, can we predict who's going to develop the worst symptoms? And can we start treating it before those, before the disease really takes over in the brain? So it's really trying to, in both concussion and Parkinson's disease, trying to figure out what conditions set up those pathological outcomes. And in vivo just means in the human, in the live person, and ex vivo means we have a model where we take the brain out of the organism, not a human, and then we can test effects there. We can hit it in different ways and look at a bit more of the cellular processes. So if you want to ask me questions about that later, I'm more than happy to talk about that. That's over.
Okay, thank you so much, Dr. Holohan. Yeah, that's actually very interesting how you were able to merge both of the answers and being able to just diagnose Parkinson's even 20 years before seeing these major symptoms. And it's probably really hard because some of those symptoms can be seen for absolutely anything, such as depression, all those types of things. But yeah, thank you so much for that. So our next couple series of questions are for Professor Bell. Now, since you work with number theory and mathematics overall, our first question for you is, how can number theory affect our daily lives, and where can we see examples of this?
Okay, you can hear me. So I'll try to be fast. I'll give just one example for time reasons. So probably the most straightforward answer I can give is things like cryptography, which, if you know, it's, how do you keep information secret, or, from attackers or eavesdroppers? And the basic principle behind it is you want to have some sort of procedure that's easy to do one way, but difficult to do the other way. And so number theory is great for these sorts of things. As an example, you can imagine you take two big numbers and you multiply them together. You can do that very quickly with a pen and paper. But if someone gives you a really big number and says, oh, can you find the two numbers that multiply together to do this? It would be a very difficult thing. And it's the same for computers, so about scales, right? So you can, that's the principle behind modern cryptography. And I'll just add, one of the interesting things is that the mathematical theories behind it were developed. They weren't developed with this application in mind. They were developed, hundreds of years beforehand, and then this application arose after the fact. So I just wanted to point that out. That's my answer to question 1.
Okay, thank you so much for that. And our second question for you, it's more of a personal question, but do you believe that there are some mathematical proofs or theories that are just redundant and unnecessarily complicated, like any theorems or formulas for anything?
Oh yeah, definitely. And I think Spiro would agree with me too. When you go to undergrad and you study mathematics, everything is incredibly polished because you're seeing things from 100 years ago or whatever, maybe more sometimes. And it's just beautiful. And a lot of people, they go to grad school and they, it's just somewhat disillusioning because, they're learning material that's maybe, 10 years old or even less sometimes. And it's just not polished, and it can be, very difficult. So it takes a while for things to get polished. And there are many examples of redundancies in the sense of, theories developed in one area and people aren't aware that this other area of mathematics is doing sort of a very similar thing, and maybe it even supersedes what's being done over there. So a lot of these connections are only realized after the fact, and mathematics is ever evolving, and a lot of what's important is only realized later on. So that's my answer, by the way.
Okay, thank you so much. Yeah, it seemed as though a lot of our panelists were agreeing with that. So we'll stick with that. And our final couple of questions are for Dr. Karagiannis. So since you work with geometry, again with mathematics, but like the geometry portion of it, our first question for you is, can your research help with like astronauts and astrophysicists launch satellites or with rocket science? And how can your research relate to theoretical physicists and quantum mechanics?
Okay, sure. So the short answer to question 1 is my own personal research is not really the type of thing that's going to be helping astronauts and astrophysicists, but certainly differential geometry as a field is essential for astronomy and astrophysics and launching satellites and all this stuff. So Einstein's theory of general relativity, which says that gravity is basically the curvature of space-time, is really just a sub-branch of differential geometry. When you're doing differential geometry in 4 dimensions with some extra assumptions, some hypotheses, then you're just doing general relativity. And so that's, of course, used all the time by modern astronomers and astrophysicists. But when Einstein came up with it in 1915, no one had any idea that this would have any practical application whatsoever, right? So the things that I'm doing now, I'm doing some geometry in 7 and 8 dimensions, which is related to physics, and I'll get to that in a minute. But whether it has any practical applications to our own society, not now, but maybe in 100 years, somebody will find it. In fact, maybe it'll take less time. Maybe one of you in the audience will find a way to practically use what I'm doing to help society. So for the other question, the question I get more often than anything else is, okay, time is the 4th dimension. What's the 5th? What's the 6th? How many are there? And the answer is, unfortunately, we've been brainwashed by society to say, okay, there's 3 dimensions of space and 1 dimension of time, and that's 4 dimensions of space-time. Then you hear something else and it blows your mind. Really, the way you should think about dimension has nothing to do with physical space or time. A dimension of an object is just how many different independent numbers you need to describe it, right? So for example, if I'm saying I'm somewhere on the surface of the Earth, I need a latitude and a longitude, right? That's 2 numbers. If I want to be really precise, I need a height above sea level. That's 3 numbers. Then I can say, what time is it? That's 4. I can say, what's the temperature? There's 5. What's the pressure outside? 6. Depending on how much data you want, how much independent data, the total number of independent parameters, that's the dimension of the space you live in. When I say live in, I mean the object you're studying. That's how many dimensions it has. So when you are studying physical space, classical physics, there are 3 dimensions of space, right? And then Einstein said, well, you really need to take time into account because it's not completely separate. It's an independent direction in some sense, but time and space mixed together. And so you have 4 dimensions. But that's, again, just when you're studying, physics. But if you're just studying some object which has a lot, some concept that has a lot of independent numbers in it, you're going to be working in a high dimensional space. So, for example, I already gave the example of the surface there. Here's another example. Some people like to watch 3D movies. Even a 2D movie is not really a 2D movie. You have two directions on the screen, but at every point on the screen you have a brightness and a contrast and a color, and then you have the sound. So even a 2D movie has a huge number of dimensions of independent parameters to describe it. Now, how does my work relate to physics? Well, some of you have heard about string theory. String theory says that the universe is not really just 4-dimensional, it's 10-dimensional, and there's these other 6 dimensions that are curled up really tightly and we can't see them. Just imagine, let's say let's say you have a very long wire which is very, very thin in cross section, right? If you're an ant walking on this wire, you might not even be able to tell that it has a cross section, a second dimension. You might just see one dimension there. So there is a way to visualize how there could be other small hidden dimensions that we can't see. And then there's something else called M theory, which says the universe is not really 10-dimensional, it's 11-dimensional. So it's the 4 space-time dimensions that we're used to, and then another 7 curled up. And what I study is the kind of spaces that can have this 7-dimensional. It's not just any old 7-dimensional space that's curled up. It has to have some special properties to predict the laws of physics as we see them. And so as a mathematician, I say, can such spaces exist? How many different kinds are there? Can we find ways to construct them? And it's great for me that physicists care about this and they're a consumer of my product, because then I get more citations for my research than I would if it was just pure math. But really, luckily for me, is I don't care if the physics is right or wrong, because I find this interesting in its own right and I would be studying it anyway. So it's just a useful byproduct that there is another field of science that really cares about what I'm doing. That's my answer.
Okay, thank you so much. That really helped break it down in a very simple way, so even our younger audience would be able to understand how the Earth works and all the different dimensions. So thank you so much for that. So it seems as though we have finished our directed question segment and we're almost at the end. We just have one more kind of personal question for all of you. And we were thinking, since Professor Bell has to leave around like 5:10, you could answer first for this question. What is one piece of advice that you'd give to a high school student hoping to go into a STEM-related career?
Oh, thanks. So the advice I would give is that is just to work hard. Well, this is so cliche to say, but it is to work hard and not give up. But I say that because a lot of people have the experience of doing very well in high school and saying, oh, this is easy and this is how it's always going to be, and then going to university and finding things suddenly become challenging. And it's easy to say, oh, I just can't do this. And a lot of times it's just a matter of putting in the time, and then suddenly things just somehow click. And I've had this experience numerous times in my life. And it's the same with research. You have to just put in the hours and just hope that the synapses will fire properly at some point. And so the advice is to just keep pushing, even when things are difficult. I do realize now that feels cliche as I say it, but that's what I'm saying. Okay, thanks.
Okay, thank you so much. That was very inspirational to me and probably to most of our attendees as well, just to keep on working hard and just trying to understand the concept and really being able to grasp more than just understanding rather than memorizing. That's a very big one that I've learned as well. So Dr. DeRosa, would you like to give our attendees maybe one piece of advice on just how to stay motivated throughout high school for someone hoping to go into a STEM related career?
Sure. So it may not be about staying motivated, but I think what I would say is that not to get too caught up in worrying about, am I making the right choice? Is this course the right course? Is this path the right path? As long as you are, still trying to learn and still making the most of whatever opportunities that you're encountering. I think, I know when I was in high school, I was so concerned about, am I in this right stream? And then when I started university, I was so concerned about am I in the right degree, and I have to finish on time, and I have to go right away into grad school. I have to go right away into, so it was like a big race. And it was like, if I'm not on the right path, I'm on the wrong path. That's kind of the mentality I had. But, looking back now, I mean, there is no right path. There's no wrong path. It's the path you're on, and the journey is just as informative as, the destination. It's probably more informative. So take advantage of the opportunities as they arise, and don't get so caught up in the end. The end is that I'm going to be a doctor, or the end is that I'm going to be a whatever. Be present in what you're doing. So when you're taking that class in high school, you may not seem like this is worth your time or whatever, but it is. You're learning and you're growing. And so don't get so worried and worked up about, getting to the next step. Be mindful and be present in what you're doing at the moment. That's my answer.
Okay, thank you so much for that. And next, Dr. Kelvin, would you like to give one piece of advice to some high school students hoping to go into a STEM-related career?
Sure. So I think it's always best to start with something that you like. So if you have a true interest in the subject, then that's the best place that you can start. Don't do something because it looks like it's going to be a prestigious career, or you're going to make a lot of money. You really have to be interested in it. Not every piece of the path will be as interesting, but when you look at everything together, you should really have a deep passion for it, because that's where your motivation will come from. The other bit of advice that I will also give is don't be afraid to ask questions and reach out for help, because there's a lot of people that I think would be interested in giving some advice, if you have specific questions, and that's including me. So you can tweet me on Twitter or comment on Instagram, or send me an email if you have questions. So I'd be happy to hear from people. And that's it.
Okay, thank you so much, Dr. Kelvin. Now, Dr. Holohan, would you like to give a piece of advice to a high school student hoping to go into a STEM-related career?
Yeah, I mean, I think so far everything that I wanted to say has been said. I agree that there are a lot of cliches, persevere, never give up, follow your passion. But I also think I want to stress what Maria had said, where don't get caught up in, this is what I'm going to do. So I'm going to be a medical doctor, so I need to take chemistry, I need to take physics. Some of the most probably worthwhile classes that I took in high school were TV productions. So I learned how to use video equipment, photography. So I learned how to work in a darkroom, and that really helped when I was developing films for Western blots and doing science, and even English literature, right? So scientists read all the time and we write all the time, and to be a good writer is a skill, and it's something that I think a lot of students think, oh, well, I don't need to do English literature because that's for, art students. But it's those opportunities that you just never know when they're going to pay off. So I think it's important to keep an open mind as you're going through your education, and then, ask people who have been through it, because a lot of us have been through paths that are not, straight. So that's my advice.
Okay, thank you so much. And it seems as though we're going a little bit over time, but we just have one more speaker. So Dr. Karagianis, would you like to give some advice to a high school student?
Sure. I think most of what I was going to say has been said by at least one of the other four speakers. So I'm gonna tell you a story from when I was in high school, and something that has stuck with me. 30 years later. We had guidance counselors. You probably have guidance counselors. We were required to go see them and tell them what we wanted to do. And, we don't know what we want to do when we're in grade 9 or 10. And then, of course, they're supposed to guide us. And that was in the phase where I wanted to do astronomy. I had passed the astronaut phase. I hadn't quite gotten into the physics phase. And back then I was severely myopic. I had -6 in both eyes. I had these big, thick glasses. Now I've had the laser surgery. But I told the guidance counselor, I want to be an astronomer. And she said, well, you can't do that because you wear glasses and you can't look at the stars. You can't see the stars, which was a really terrible answer. Luckily, I knew that she didn't know what she was talking about, and I ignored it. But I wondered how many other students got bad advice and took it, right? And followed that. So what I would tell you is, don't let anybody tell you that you can't do something, because you can. And you guys have much more resources than we did when we were young. You can look things up online. You can find out what it takes to do what you need to do, and you can do it, right? So anyone who says, oh, this is not the right path for you, if it's what you want to do, just ignore it and do it. That's what I would say.
Okay, thank you so much. That's actually very inspirational, because I bet a lot of us have heard some like horror stories from our guidance counselors about not really being on our side for our dream or our goal. So thank you so much for that. So it seems as though we have reached almost the end of our presentation. So now it's time for the Q&A segment. So attendees, it's actually your turn. So if you have any questions for our panelists today, you can just drop them in the chat box below in the Google Meet call. And if you're watching from the live stream, you can also just drop it in the live chat below, and our executive team will monitor them and make sure our panelists answer them. So thank you so much for our panelists for taking time out of your day to come and speak at our conference and just being able to educate high school students about this amazing career of STEM. And attendees, thank you so much for the amazing turnout and the outpouring support. We totally weren't expecting all of it, and we just like to thank all of you so much. So you guys can stay on maybe for the next 2 to 3-ish minutes to answer any questions. And panelists, so our speakers, if you're comfortable, if you want, you could drop any type of social media or your email in the chat box below. So if any of our attendees have any types of questions, they can just email you any questions they have. And yeah, so thank you everyone so much. You guys can just stay for 2 to 3 more minutes because I don't see that many questions. And yeah, thank you so much, everyone.
So it does seem that we have a question from Harry Wang, and it's asking that, not to anyone in specific, but how do we analyze the theorized high-dimensional geometries curled up in molecules? So if any of the panelists would like to answer this, go ahead.
Yeah, maybe I'll take that one.
Okay. Go ahead. No? Not sure what analyze means here, but we have a lot of tools for studying high dimensional geometries, and here's an example where if we got some chemists working with differential geometers, I'm sure we'll make a lot more progress than either side does on their own, and there are a lot of people doing that. But unfortunately, I don't have the knowledge to give a better answer to that question.
Dr. DeRosa, I had a question. So what are aptamers made out of?
Great question. So aptamers are DNA. So one of the building blocks of life, or RNA. So it's synthetic though. So we can make this, we have an instrument in our lab where we can make synthetic DNA and synthetic RNA. And so it's basically really, really short pieces. You know, in our genome, DNA would be, you know, all these billions of base pairs. On this instrument, we make a piece of DNA. It's 100 bases long, so 100 building blocks long. So much, much shorter. But other than that, it's the same chemical structure, it's the same behavior as DNA or RNA anywhere else, and that's why it can have these interesting biological properties. It can bind to things like antibodies would, can help us to detect, can help interfere with processes, we can use it for therapy. So DNA or RNA typically.
That's great, thank you. And I think someone had a question for Dr. Kelvin asking if she's in a lab, and I think she answered that in the chat, so that's pretty interesting. And Dr. Holohan, so Simran's asking, what inspired you to go into studying Parkinson's disease?
Sorry, my phone was ringing. It was, so actually Maria and I were studying dopamine, and we were trying to attach aptamers to dopamine, which is very challenging because dopamine is very soluble and floats all around the brain. So what we started thinking was, well, what are some disorders that are associated with dopamine? And we kind of just kept building up and building up back to the protein that is, shows pathological responses in Parkinson's disease. And we were able to, well, Maria was able to design an aptamer that could bind to that protein. And so we just started going from there. I mean, I've always had an interest in neurodegenerative diseases. I'm more from the memory side and Alzheimer's disease, but Parkinson's disease really kind of took off when we had a tangible target. So it just kind of went from there, more experimental findings than anything.
Thank you so much. So Dr. Holohan, we have another question for you from Harry Wang. He's asking, how much energy does the average brain consume per day, and is there a percentage breakdown as to what portion of the total energy goes to what?
Yes, there is, and I can't think of it right offhand. We often look at this in terms of, blood flow to the brain. It's energetically, or it's metabolically very active. So I'm not sure how much it consumes per day. The total energy that goes into the brain, I'm sure I know this somewhere. I can't think of it right off the top of my head. We can always have a conversation afterwards about this. And actually, relation to stroke, it's an important topic because there's a lot of oxygen usage in the brain. And when you cut off that oxygen, when there's lack of blood flow, then the brain starts dying off and other organs start to fail.
So we actually have a question from a parent who asked, how do we help youth thrive in the remote learning mode in the well future? I'm not really sure what exactly that is supposed to mean, but if one of you guys would like to try to answer that.
I can jump in. So I'm chair of the chemistry department, and we're right now trying to figure out exactly how, we've been doing this all summer, how are we going to engage with students in this remote kind of environment, especially when we're used to teaching students in labs. And what I can assure you is that the profs are ready to engage with the students no matter what the format, if it's online or eventually when it's in person. So I think the key for the students is to take advantage of the resources that are provided, and don't be afraid to contact the prof and to engage in whatever virtual sessions that they want to have, so that they can really just make the connections that you can, even if it is in a strange environment. So I know that applies to university. I think it also applies to high school. So if you're still in high school, your teachers there, they've been working really hard to try to make sure that they can, you can meet your learning objectives in this strange world. So don't be shy to reach out to them and, ask questions, because they are there for you, and that's, they're ready for those questions. So that's my advice, I think.
Thank you so much for your great advice. I feel like that really helps high school students really get a great understanding on how to really balance their school and personal life in general. There is another question for approaching professors. So Aletta wanted to know if there's any advice on approaching professors or scientists for internship positions or job shadowing opportunities. So would any of you like to answer that?
I can say a few words. Don't be afraid of us. I've had a lot of students who are really intimidated to come and talk to the professor for whatever reason. We're normal people, just like the rest of us. Just email us, right? Or knock on our, and once we get back into our buildings, come and knock on our office door. And unless, you know, we're busy with something that's time sensitive, we'll be happy to talk to you. So it's exactly the way you would look for a job anywhere else, right? You go and you ask and you talk to people.
All right, so we have a question for Dr. Kelvin. I'm not sure if she's here right now. Okay, so we can just skip to the next question if there is one.
I don't think there are any more questions, but I could direct this question for Dr. Calvin to another panelist, if that is okay. So Harry Wang again is asking, I saw air tubes on the suits that researchers are wearing in the contaminant labs. How do they work and are they airtight? So would any panelist would like to answer that, or can any of you?
I don't think we can answer, but I will say that I know that if she's at Vito Lab, this is a class 3 biocontainment facility, and this is the, you know, there's only one level higher in terms of being able to deal with very dangerous viruses. So this is a very, very unique facility, and they wear the protective equipment to make sure that they're able to work with those things. So I'm going to assume it's airtight because they're working with very serious pathogens. And like I said, there's only one level that's higher. There's one in Winnipeg, level 4 biocontainment facility for working with the most dangerous viruses. So actually,
Yeah,
Canada's a leader in this. Yeah.
I'd probably say they're like a scuba gear, right? So they're self-contained breathing apparatus, so nothing gets in, and you breathe everything within that suit because viruses are very small, and if it's not airtight from the outside, then, you know, you're in trouble.
Thank you so much, guys. I believe there aren't any more questions. So
I had one more
on behalf
question.
of everyone, we want to thank all of you guys for joining, and thank you for participating in the first ever STEMPOWER webinar. So thank you so much.
Yeah, we're planning on actually holding a couple more conferences, maybe once every month, maybe, with having different specialists from different fields from STEM. So we're really excited to be able to see all of you again sometime then. And yeah, just thank you so much for taking time out of your days for attending. And we hope you all stay safe and have a great day during these very difficult times.
Yeah, thank you for organizing. This was really great.
That was great.
Thank you
Thanks,
so much.
everyone.
Thank you. Bye.
Bye.
Thank you.
Bye.
Bye.
Thank you.